Okay, so today we're going to continue talking about populations and the factors that affect how populations grow or don't grow. So let's jump right in. Here. Okay, so today what we're talking about is carrying capacity and those factors that limit growth. So we know that no population can grow indefinitely. There are lots of limiting factors on a population. So if we think about autotrophs or photosynthetic organisms, obviously light is going to be a limiting factor. It's also limiting for other organisms as well, but particularly for those autotrophs. Water, of course, is a huge limiting factor, both for plants and for animals. Space, obviously, organisms need a certain amount of space to grow. Competition for resources, whether those resources are nutrients or other organisms. And then, of course, predation. So the seal population is very definitely limited by the shark population. So in order to talk about carrying capacity, let's talk a little bit about, and disease, of course, sorry. Let's talk about the intrinsic rate of increase. So this is what we abbreviate R. So the intrinsic rate of increase is the rate at which a population would grow if it had unlimited resource. So when we talk about R selected species, we are talking about those species that if they had an unlimited resource, that they would grow at this sort of a rate. And this is what we call an exponential growth rate. So again, intrinsic rate of increase is the rate of population growth if there are unlimited resources. So what are some characteristics of rapidly growing populations? Well, they reproduce early in life. For example, here we have mice. Actually, that's a rat. So we have a rat which reproduces early in life. We also have a short amount of time between generations. So again, insects are a great example of rapidly growing populations. And then they have long reproductive lives. So they reproduce early, they reproduce often. So we have a short generation time. And then we can reproduce many times in that lifespan. And then the last thing that affects or is a characteristic of a rapidly growing population is the number of offspring. So the scientific term for the number of offspring is fecundity. If you have many offspring, then you have a high fecundity. Okay, so these are rapidly growing populations. Reproduce early in life, reproduce often, reproduce for a long time, and have a lot of offspring each time they reproduce. But we know that organisms don't have unlimited resources. And so when they do have limited resources, we call that environmental resistance. So those are the factors that limit growth. So carrying capacity is determined by biotic potential, so that R factor, that's the maximum reproductive rate, and the factors that limit growth. As a population approaches carrying capacity, growth rate is going to decrease because as resources become more scarce, mortality is going to increase. The number of offspring per reproductive cycle is going to decrease because there's less energy available to create offspring. And so as a population reaches carrying capacity, growth rate is going to decrease. So we know that this exponential growth cannot last indefinitely. And so We only see this type of a growth rate when there's a new environment or when a bunch of resources are suddenly added to an environment. Most of the time, what we see is an S-shaped curve or a logistic growth curve. And this is that initially you see this exponential increase. And then as we start to get closer to carrying capacity, the rate is going to slow down. So exponential at the beginning, and then it becomes S-shaped. This is the point right here in the middle of the S curve where the reproductive rate is the highest, and then it starts to slow. So make sure that you understand that that inflection point there is the point of maximum growth. Now, rarely do we actually see a perfect sigmoidal curve or an S curve. What we very often see is something like this, where we have exponential growth at the beginning, and then we shoot past the carrying capacity. Now, how can you go past carrying capacity? Well, reproductive response is always going to lag behind a little bit, especially depending on that generation time. And so, as when there are lots and lots of resources, there's going to be lots of reproduction. And then when the number of individuals exceeds the number of resources, we call that an overshoot. And there's going to be a correction. There's going to be what we call a dieback. So we have lots of organisms and they go past carrying capacity. There's not going to be enough resources for all of those individuals. And so many of them are going to die. And we're going to come back down below carrying capacity. And then generally in most populations, you're going to see this oscillation around carrying capacity so that as many of the individuals die off and resources become more available, then the population is going to increase again, and then we're going to have that die off again. And so we tend to oscillate around this plateau, and that plateau is carrying capacity. So be able to recognize this on a graph. Okay, let's talk about the exponential growth equation. So this is the exponential growth equation. N sub t is equal to n sub naught times e raised to r times t. So when we talk about this n sub naught is the initial population size. So this is how many individuals there are in the population to begin with. R is the rate of growth. This is going to be expressed as a percentage or as a decimal. T is the amount of time, and that's going to be correlated to that growth rate. So if the growth rate is annual, then T should be in years. If the growth rate is per month, then T should be in months. E is Euler's constant. You're probably familiar with E from your math class. It's approximately 2.7. And then N sub T is going to be the final population size. So the final population size is going to depend on the initial population size, as well as the growth rate and the amount of time at which the population has been growing. This is the same equation for calculating compound interest. So it's anything that grows at an exponential rate. So let's do a practice problem. If we have a population of mice that has an initial population size of 20 individuals, so our n sub naught is going to be 20. The intrinsic growth rate for mice is 0.2 or 20%. And it asks us to predict the size of the mouse population 5 years from now. Okay, so we have R is 0.2, T is 5, N sub naught is 20, and E is 2.7. So when we plug all of that into our equation, we get that at the end of 5 years, there's going to be 54.4 mice. Now we know that that is assuming that none of the original mice died, which in 5 years is probably not a very good assumption, but this is a general idea. You are not going to have to calculate this on your exam. However, you should know how to calculate it, and you should understand how increasing time or increasing the rate of reproduction is going to affect the overall result. Okay, so if we did this again for 10 years, we would change this 5 to a 10. So instead of 2.7 being raised to the first power, we would have 2.7 squared times 20. And you can see that that would increase this number substantially. We would have 2.7 squared. And so at the end of 10 years, we would have 147.8 mice, which is more than twice as many mice, right? Even though it's twice the amount of time, it's well more than twice the amount of mice. And we'll do this one more time for 20 years. So now we have 2.7 to the fourth power, and we have 1,092 mice. Okay, so exponential growth definitely changes substantially. It does not double it doubles in the same amount of time. And we're going to talk about something called the rule of 70 in a little bit. If you're asked to calculate change over time, take the first number that you have, the final number, and divide by the amount of time as a percentage. Okay, let's talk about density dependent factors. So when we talk about these limiting factors, we talked about density dependent and density independent. So density dependent factors are those that change their intensity, change their limitation ability, depending on the density of the population. So these are things like competition, predation, disease, parasitism. So we very often see this sort of cyclical pattern, so that as the population of the prey increases, well, if you have more prey, then you can have more predators. And as the predator level increases, that's going to decrease the number of prey. And so we get this offset cyclical pattern. When we have density independent factors, we're talking about those that the number of individuals is irrelevant to how much it affects the population. So some natural causes of this are things like floods, hurricanes, fire. When we talk about human caused or anthropogenic, pollution and habitat destruction. So it doesn't matter whether there's a lot of mice or a few mice. If we destroy the habitat, it's still going to have the same impact on the population. So 4 kinds of population fluctuations. We have stable fluctuations. So that means that's that oscillation that we talked about that's going to fluctuate above and below carrying capacity, but it's going to stay pretty close to that carrying capacity. So this tends to occur in places like the tropical rainforest, where temperatures and rainfall stay steady, and so the environment is very consistent. We're going to have a very stable population. It's just going to fluctuate around carrying capacity. On the other hand, we can have what's called an eruptive fluctuation. So this is one where it's normally stable, but it'll sometimes explode and then crash. So algae are a great example of this due to seasonal changes, nutrient availability. Insects also, if you think about spring and fall, we tend to have explosions in our mosquito populations, but then they tend to stay steady the rest of the time. Then we have our cyclic population fluctuations. So these rise and fall in a predictable pattern. So very often your predator-prey cycles fall into this pattern. And then your last one is those irregular population fluctuations. There's not a recurring pattern to it. This could be chaos in the system, or it could just be one of the other 3 types of fluctuations that we just don't understand yet. We don't have enough data. As always, if you have any questions, please let me know.